What's up guys, so today we're going to be talking about hot air and how you can decide what temperatures and what airspeed to use with your hot air station when you're working on various components and various boards. I'm going to be visualizing a few things for you with the new thermal camera here, and we're going to see how various nozzles and airspeed and temperatures impact different kinds of boards. I made a video going over iron temperatures, so I'll have a link for that in the description, and you guys had expressed interest in me making a follow-up regarding the same kind of topic but with hot air stations, so that's what we're doing today. If you guys are interested in the thermal camera I'm using for this video, I'll have a link in the description along with a coupon code where you can get 8% off of the order. I'm really enjoying this thing so far. I'll also put a link to the review video I made for this thermal camera in the description as well. Now, all of the temperatures I'm going to be mentioning in this video are going to be in Celsius. And I do want to stress that, as with any other tool, your hot air station is going to behave differently from mine. And the temperatures I'm mentioning in this video are not strict rules by any means. And part of the reason I wanted to make this video and the iron temperature video is to sort of break down the fear of messing with your temperatures to see what works. I think when you're just getting started, it's really important to see what does break components and what doesn't, especially with your specific tools. But at the same time, I do want to give you guys some starting points for how to approach what kind of temperatures and airspeed you should be using when you're using your hot air station. Now, I know there's only generally two knobs on the hot air station. There's airspeed and temperature, but there's actually like 5 different variables you need to be thinking about with your hot air station. So obviously temperature and airspeed are 2 of them. You also have the size of nozzle you're using or lack of nozzle, and you have the distance from the board, and then you have the angle at which you're holding the hot air. And these are all really important factors for how that hot air is going to impact the board and the components that you're heating up. So let's start with the decision of temperature. Generally speaking, I'll use anywhere from 100 to like 200 degrees Celsius in order to liquefy flux and help me clean boards. Hot air can be a really useful tool for cleaning and things like that. Or if you're trying to remove adhesives, from 200 to about 350 degrees Celsius are like my preheating temperatures. This is usually what I'll use to preheat boards. Especially if you have a large board like this, you're definitely going to want to preheat the board before you actually begin to turn the temperature up and try to liquefy the solder. I would say maybe unless it's a small component and or it's using leaded solder to fix it to the board, because there's times where you don't need to put as much heat into those smaller components or components with leaded solder on them. But no matter what, I always recommend preheating things. You can use your hot air station to preheat. You don't always need like a dedicated preheater. Preheaters are really nice if you're removing multiple components or if you're removing a very large component. For example, if I were to be removing the SoC here, I would definitely want to preheat a large portion of the board so you don't start warping the board and delaminating the board when you go to start using those higher temperatures that you need to get this large BGA chip off that has unleaded solder balls underneath it. Board size and thickness is not the only consideration you need to take into account when deciding temperature. You also need to think about whether or not the component has leaded or unleaded solder on it. Leaded solder has a lower melting temperature than unleaded solder, and it melts at around 183 to 190 degrees Celsius. And then you have unleaded solder, and that melts at anywhere between like 217 and 227 degrees Celsius. So generally speaking, it's about a 30 degree Celsius difference between the unleaded and leaded solder, and while that doesn't sound like much, that 30 degrees Celsius difference really makes a huge difference when you're going to try to remove components off of a board that has a lot of thermal mass. So all that being said, generally speaking, I'll use anywhere from like 350 degrees Celsius to about 400 degrees Celsius for leaded solder, because it has that lower melting temperature. And for unleaded solder, which melts at the higher temperature, I will generally use anywhere from 375 degrees Celsius to 450 degrees Celsius. So these are just some good starting ranges depending on what you're working with. Again, this is going to depend on your specific hot air station and how it gets heat into the board. And it's also going to rely on lots of other factors, like for example, your airspeed. So airspeed is actually a really important decision when you are working with hot air. The reason for this is the airspeed you choose is going to dictate how fast that 350 degrees Celsius, for example, is going to make its way into the board. Let me demonstrate that for a second. I have 350 degrees Celsius set on my hot air station, and right now I have it at the lowest possible airspeed. And let's take a look at what it's going to take to actually get this heat into the board. So you can see it's starting to heat up, but honestly, it's not really spreading out that much. And if I take my hot air away, you can see it only got up to about 82 degrees Celsius in the red spot there in the middle, and now it's already going down. Now let's see what happens if I boost my airspeed to 100%. So you can see the heat spot grows significantly faster than it did when I was using the lower airspeed. And I'm going to take the hot air station away now, and you can see it's already at 100 plus degrees Celsius compared to before. So I did not change the temperature of my hot air station at all. I just changed the airspeed. You could see how quickly the heat spread throughout the board, and you could also see that it got to a higher temperature than the lower airspeed did. So now we're just going to cool off the board. You can see how nicely this thing cools the board off. It's already like cold. You can see with the thermal camera as well that the heat just disappeared. I love this thing for being able to test boards right after having soldered on them. Definitely recommend this thing. I'll put a link in the description for it. One of the things I want to point out with SMD components, especially BGA chips and things like these, where the solder balls are actually underneath the components themselves, is that there's a significant difference between the component temperature, the board temperature, and the temperature that's actually going into the solder balls themselves. This is one of the main reasons why preheating is really important when you're doing BGA rework. And this is because you're not trying to heat the component. You're trying to melt the solder underneath the component. And you have to recognize that that solder is touching two things. It's touching, yes, the component, but it's also touching a much larger thing, which is the board itself. And the board itself is a lot more difficult to heat than the component. So one of the mistakes a lot of beginners make when they're going to use the hot air station is they're trying to put enough heat into the component instead of enough heat into the board. So to demonstrate this, I'm going to use no nozzle, and I'm going to use 350 degrees Celsius. And I'm just going to try to heat this whole south bridge up here without any preheating, and watch what happens. All right, so I've gone ahead and heated that up for a little while, and you can see this chip is now at about 120 degrees Celsius. But now look what happens if I flip the board. What is the temperature underneath the board here? The temperature under here is only like 100 degrees Celsius. So the component here is actually a lot warmer than the actual board itself by about, 10 to 20 degrees Celsius. This becomes a problem when you're trying to remove this chip, because you're going to end up putting a lot more heat into the actual chip than you are going to be putting into the solder balls themselves that you're trying to melt. So all that to say is, especially with BGA rework or even smaller surface mounted components like MOSFETs and things on a board that is large and thick, you're really going to want to be preheating the board, whether it be from the bottom or the top of the board with the hot air station or by using a dedicated preheating station. If you're planning on doing a lot of BGA rework, I highly recommend you get a dedicated preheating station like this one that is going to help you preheat the entire board or a large area of the board so that you can more easily remove chips like this south bridge here without having to heat the south bridge up like way too much and killing it. You have to understand that when you're working with hot air versus a soldering iron, you're going to be putting a lot more heat into the components and the board, and prolonged heat at higher temperatures can really damage chips very quickly and can also do things like popcorn or delaminate the board. So you also have to take into account how long you are subjecting the components and the board to that heat, because going ahead and just blasting the south bridge with 450 degrees Celsius without preheating the board is a really great path to holding that heat for way too long on that component and very likely killing the component and or delaminating the board. It's pretty amazing what preheating the board to about 100 degrees Celsius will do for how long you have to use the hot air. You're going to have to use your hot air for a lot less time to get this thing off when you preheat this board, even just to 100 degrees Celsius. And on top of that, I would preheat the top of the board here as well with the hot air by not going as close to the board at first and then sort of working my way in and finally hitting the chip with that really hot air for a short period of time. So I really want to stress this point of component temperature versus board temperature and how important it is when you're working with a hot air station. And the same thing goes here as far as board size and thickness goes. As I explained with the soldering iron, you're going to have a harder time getting enough heat into a larger board like this than you are going to with a smaller one like this. So just to stress this point, I've put my nozzle back on the hot air station here. And let me show you with the thermal camera, if I just heat the south bridge up right here with the nozzle on it, what's going to happen on this board versus the similarly sized SoC on the switchboard. All right, so I've heated this for about 20 seconds and you can see the majority of the heat is just in the component itself, and the board itself is basically not preheated at all. So now if I heat the similarly sized SoC on the switchboard, which is smaller and thinner than this Xbox One board here, watch what is going to happen. So check this out. I just did the exact same amount of time on the SoC here, and you can see this whole entire board is essentially preheated except for this little area down here. So this whole area around the SoC, even though I only heated the SoC itself, the entire board got preheated from just those 20 seconds versus over here where it was really just that component that got warm and a little bit around the component. Not nearly as much of the board got warm. So board size and thickness is also a really important thing to consider when you're deciding what kind of temperatures and airspeed to use and how close to put the hot air, as well as what kind of nozzle sizes to use. So the next thing to take into account is the size of the nozzle you're using, and this interacts very closely with airspeed, because if you use a smaller nozzle, it's It's going to restrict that airflow, and it's going to be a lot more intense, that same airspeed coming out of the nozzle, than it is when you have a larger nozzle or no nozzle. The other thing to note with the nozzle size is that it's going to heat a larger area if you have a larger nozzle than it is with the smaller nozzles. So this impacts both the area that it's going to heat and how much airspeed is coming out at that same airspeed setting on your hot air station. You also have to keep in mind that some of the nozzles are shorter than other ones. For example, these two are kind of a similar size, but you can see the length of the bent nozzle here is much longer. It's almost twice as long as the straight nozzle. This is something to take into account because this means that the hot air coming out of the nozzle here is twice as far away from the heating element as the hot air coming out of the nozzle here. So the length of the nozzle really can make a difference as well. And if you're ever having trouble getting something off with a bent nozzle, I actually recommend trying to switch to the same sized straight nozzle, and preferably one that's like a little shorter like this. That can really help sometimes get enough heat into the board versus your bent nozzle. So let's do another quick demonstration of how a larger nozzle will impact things versus a smaller one. So let's start with a smaller one like this, for example. And I'm going to keep my hot air station at 350 degrees Celsius and keep it at 50% airspeed for the whole test here. So we're going to turn it on. I'm going to let it get up to temperature here. All right, so let's start heating the same area here with the small nozzle. Cool, and you can see that got up to about 90 degrees Celsius with the smaller nozzle. And let's cool the board down again. So let's try using the hot air station with no nozzle now. And I'm not going to hold this as close because like we talked about, this nozzle puts distance between the heating element and the board. So I'm going to mimic the same distance with the hot air station by holding it a little bit higher up. And let's see how this impacts the board. So you can see it's taking longer to heat the board, but it is going to heat a wider area as it gets up to temperature. And this is because the airspeed is reduced even at the same airspeed settings when you have no nozzle versus when you have one. But you can see it is heating a much wider area than the nozzle was. And now if we take this away, you can see it's at like, I don't know, 110 degrees Celsius. So I hope you can see that the nozzle that you choose really does impact how the heat gets transferred from the heating element in the hot air station to the board or to the components on the board. What I would recommend, and this is what I do, is pick a nice medium-sized nozzle that's going to be very versatile for lots of things, and just keep that as sort of like a default on your hot air station and get used to it. Especially if you're just starting, I don't recommend switching your nozzle size a whole lot. This is going to confuse you because your hot air station is going to behave very differently with all these nozzle sizes. Whereas if you just stick with a nice medium-sized one like this, you're going to be able to use it for a lot of things, and you're going to be able to get used to your specific hot air station and how to effectively get heat into the board. Now, obviously, if you're working on larger chips, for example, this Southbridge on this Xbox One board right here, this nozzle size here is not going to do you much good. So what I recommend for that sort of stuff is instead of switching to like a big nozzle size, just remove your nozzle entirely from the hot air station and get used to how your hot air station behaves with no nozzle on it as well. Honestly, personally, for 90% of things, I can either use this nozzle or no nozzle at all, and I can generally make it work for almost any chip size I need to take off or put on the board. It's very, very rare you're going to see me use any of these. I recommend just picking a nice versatile size and putting all of these in a drawer for later use when you're more comfortable with your hot air station. The other thing to take into account when you have no nozzle is your airspeed is significantly reduced. So generally, I will compensate for that by going to about 80 to 100% airspeed. So if the point of me taking off the nozzle is to heat a wider area, I can't just take the nozzle off. I have to take the nozzle off and boost my airspeed. And generally without a nozzle, at least with my hot air station, you're not going to be blowing stuff around with 100% airspeed. Whereas with the nozzle, higher airspeeds like that are going to like blow components all over the place. So again, just play with your tools and get a good idea for what works for you airspeed wise when you have a nozzle versus no nozzle. I'll also mention that if you're having issues with blowing components around because your airspeed is too high, all you have to do is lower the airspeed so you're not blowing things around and compensate for that by turning the temperature up. Especially as you get more comfortable with your specific hot air station, you're going to find yourself using higher and higher temperatures. The only trick to that is you're going to want to sort of like work quickly so you're not exposing the components and the board to heat for a long period of time. But yeah, temperature and airspeed really work hand in hand. So if you need to compensate for one, you can crank up the other one. And balancing those two can be a really, really great tool to accomplish what you need. So next I want to talk about the distance that you hold your hot air station away from the board. And this is a really, really useful tool you can use to control the area that you're putting the heat into and how much heat you're actually putting into the board without even touching the airspeed or the temperature on your hot air station. You can use the same exact airspeed and temperature and have very different effects by holding the hot air station further from the board or closer to the board. So when you hold the hot air station further from the board, it can be really nice to sort of preheat things. Instead of having to go change your temperature down to like 250 Celsius, you can keep it at 350, 375. And instead, you can just pull back from the board. And what that's going to be doing is it's going to be heating a wider area than when you're closer. It's also going to reduce the airspeed of the air actually hitting the board, as well as the temperature of the air hitting the board. So the temperature coming out of the nozzle up here is much higher than the air when it actually hits the board when you're further away from the board like this. So let's see how that looks. I'm going to just sort of hold the hot air higher up, and you'll see how wide of an area this begins to heat. You can see even though I have like a medium nozzle on the hot air station, it's heating this sort of wider area. But if I remove the hot air, you can see it's actually not that hot. It's only about like 60 degrees Celsius, even though I have my hot air station set to 350 degrees Celsius. And this is really nice for preheating. You can see a lot of the area around where I was heating is preheated, and then I could come in closer with that same hot air and heat that more concentrated area to actually pull the component off. A preheated board is much easier to pull components off and work with than one that is not preheated. All right, so I've cooled the board down again, and now I'm going to hold the hot air station really close to the board without having changed any temperature or airspeed settings. So you can see the heat is staying in a more concentrated area than it was before, and you can see when I pull away, it's much hotter. It's at like 115 degrees Celsius versus the 60 degrees Celsius from before. So hopefully you can see that the distance away from the board really impacts how much the temperature of your hot air station and airspeed is actually impacting things, and you can use that to your advantage to preheat things before you actually come in and take them off or reflow them or whatever you're trying to do. One thing I'll quickly cover is the angle. This actually makes a big difference. I think these bent nozzles can sometimes give you a bad habit of resting your wrist. And look at what happens when I do that. The nozzle is actually like at an angle and it's not actually straight up and down. When you're heating the board, you really want to get as perpendicular to the board as possible with the nozzle. And the reason for this is it's going to make the hot air a lot more concentrated in the area that you're actually attempting to heat up, versus just sort of spreading out through the board in the direction that the nozzle is pointing. I think when you have a straight nozzle or no nozzle like this, it's a lot easier to hold it correctly because you're not going to be, tempted to use it like this. So if you're using a bent nozzle like this, just make sure to put enough pressure with your fingers on the top so that it actually makes the nozzle perpendicular to the board and heats the area that you're actually trying to heat. So again, we can give a quick demonstration of this. If I hold it at an angle like this, you'll be able to see that it's not like a perfect circle there, and it's actually spreading the heat towards those chips and not on the area that I'm actually pointing at, if that makes sense. And now if I remove the hot air station, you can see how much it heated up and to the right of where I was actually trying to heat. And I got the board cooled down again here, and we're going to do the exact same thing, but I'm going to go perpendicular to the board, and you can see it's not spreading out in any way, and it's actually going to be a lot more impactful at heating that specific spot that I'm pointing at. You can see that got up to like 113 degrees Celsius, and it's a lot more uniform where I was pointing it versus up towards these chips over here. And one other little trick I'll point out here is that you can see we have these little plastic components right here pretty close to the Southbridge chip. So if I actually was pulling this off of the board, I would actually cover this first in some aluminum tape. Aluminum tape or like duct sealing tape like this is really useful and handy for shielding components from heat when you're trying to apply heat to something close by. And I just take my ceramic scissors and cut a nice big chunk of the tape off. And then you don't have to deal with like aluminum foil and taping it down everywhere with Kapton tape. You can just use this stuff. And it works really great to keep its shape, and it sticks to the board. And now I don't have to worry nearly as much about heating up these plastic components. So you don't want to be like directly heating on this tape here for a long period of time. But I've never actually had any issues with melting components using this stuff, as long as you're, using common sense. I'll also do the same thing for these little FBC connectors, or like the battery connector here, or these speaker connections here. These are all plastic, so covering these up is always really important if you're working with hot air nearby. And I just find that aluminum tape is really convenient for that. So I just wanted to give that little tip. So I hope this demonstration was interesting and helpful for some of you guys. Overall, I would say the goal of using hot air is to heat things for as little time as possible. So choosing your temperature and your airspeed and the distance away from the board and preheating and all those things can really help to minimize the amount of time that you're exposing the components and the board to high heat. So I hope this was a helpful demonstration for some of you guys out there. I'd really love to put out more tutorial style content. I have plans to go over circuit designs that you will find commonly in schematics and sort of break down how exactly they work and how you can diagnose certain faults with them. I also plan to make more videos like this where I break down how I recommend using specific tools. So if you guys have any specific recommendations, please throw them in the comments. I would love to hear them, and I'll definitely add some of these suggestions to my list. So I appreciate you guys for watching, and I will see you in the next video. Peace.